In the name of God, hi, my name is Mohammad Mahdi Mohsenzadeh. In this project, I'm going to design and simulate two conventional converters with closed loop control, which are voltage mode control and average current mode control. First of all, I have to mention that after my second semester in my master's program, I decided to be acquainted with controlling converters, so I decided to work on these conventional converters. I chose buck and boost converter, and I just simulated these converters, but I couldn't implement them because I was not allowed to use laboratory at that time. Now I'm going to speak about this converter. First of all, we are going to work on the boost converter. As you can see in this picture, I used PSpice software to simulate this converter. This closed loop boost converter was my first experience, so it's not good, I think, and I have two another projects which are better than this one. First of all, I have to talk about this conventional boost converter here. As you can see, I have input voltage. It's a DC power supply, and on its output port, I have 9 volts, and input voltage is 6 volts. With this converter, I used these parameters of this converter to obtain its small signal, and after that transfer function, and I designed the second type compensator for this converter. As you can see, I have two resistors here which are connected in series, and after 12 minutes this resistor is going to be bypassed, and only one resistor we have on its output port, so it means that the output power is going to be doubled. As you can see, I'm sampling the output voltage with this voltage divider, and I'm comparing it with this voltage here, and this op amp is going to make an error signal, and is going to be compared with this triangular waveform. This is a triangular waveform, and this is an element which is comparing the error signal and this triangular wave, and after that the output of this element is going to be pulse for this MOSFET. It means that this element is going to create signals for this converter. When the error signal is higher than this triangular waveform, the output voltage should be 10. Okay, and when the error signal is less than this triangle waveform, the output voltage should be 0. So we have pulse on its output port. So I'm going to show you the result of this simulation. As you can see, after about 7 milliseconds, this converter can stabilize 9 volts on its output port, and at this time, at 12 milliseconds, the output power is changed and the output load is changed, so the converter is going to stabilize that voltage 9 volts on its output port, but it takes a lot of time for that. Because it was my first experience, and I decided to be acquainted with controlling converters. I designed and simulated this converter, so it's not very good, and it's not good, I think, but I designed another converter here which is more complicated than this one, and in this project I designed a buck converter. It's a buck converter with all components, and all of them are analog components. There is no digital controller here. All of the controller here is analog. First of all, I have to talk about this converter. As you can see, I have the DC supply for input port, and I designed input filter because we have a series MOSFET. We have a MOSFET in series connection with input DC power supply, so the input current should be positive. So we need to design an input filter to make this input current DC, and we have this, the output filter, and again we have this series connection of resistors here. At time 5 milliseconds, this switch is going to be connected, and this resistor is going to be bypassed. Now we have another second type compensator here, but we have some differences in comparison to that boost converter. Again, we have a voltage divider, okay, but the referenced voltage is going to be created by this circuit, R22, R23, and D4. D4 is a diode, Zener diode. So this is coming from out of this voltage regulator. 15 volt is going to be here, and after that voltage divider and Zener diode. So the output voltage reference should be about 12 volts. The desired output voltage should be 12 volts, and this converter must stabilize 12 volts on its output port. And we have this analog op amp. Again, instead of this element, I'm using this circuit to create signals for this switch. As you can see, I'm using an isolated gate driver here, and it is very clear. So we have a triangle waveform here, and error signal goes to this port, and it's going to be compared with this, and output we have signals for driving this MOSFET. So, and another important thing that I can mention right now, it's about this and this, these resistors R12 and R13. I read a paper about that for mitigating the bias current of this op amp. We can use these series these resistors and the negative and positive port or negative and positive pin of this op amp. So we can with this one R9, R12 and R13, we can mitigate that, or maybe we can use these resistors to make this bias current 0 for this one, this part. We don't want to see the drop voltage of this resistor, so we have to find a suitable value for this resistor to do not see this drop voltage, because if current flows to this pin of this op amp, okay, we have a drop voltage, and the output voltage is not going to be regulated on 12 volts. So, and I use the circuit here, regulator, to provide these op amps power supply. So it is very clear. I'm going to show you the output voltage and the input current of this converter. As you can see, the output voltage, it's here. Okay, again, this converter is not designed properly, because we have 10 amps in input current, so we have to reduce it, and I have to work on its control. But this is my second experience in designing and controlling conventional converter for my projects that I did after this project that I'm talking about. I designed a suitable compensator for that, and I do not have any inrush current or very high value current in my input ports. As you can see, this converter can stabilize output voltage on 12 volts properly, and here the output load is changed, as you can see. Okay, output load is changed, and now we can see that this converter and this compensator can stabilize the output voltage again on 12 watts very properly. Okay, this is the ripple of input current, it's DC, and that's it. So now this converter is controlled with voltage mode controller. This boost converter is controlled with voltage mode controller, but in this converter I used average current mode controller. For this controller we need to sample the input, we need to sample this inductor current. So I use this shunt resistor and I'm sampling this current with isolated element here, and I have two control loop. This is the voltage loop control and this is the current loop control, and the voltage loop control signal is going to be compared this and the output sample of this inductor's current. As you can see here, the signal is going to be compared with that, and after that we have error signal which is going to be compared with this triangle wave, and after that we have a signal for driving this MOSFET. As you can see, this converter is completely similar to this converter. Okay, and about the second type compensator, again we have it here, but the value of capacitor and resistors are changed. So we have those resistors in this project, we have them here again, and again we have this series connection of these resistors. So I'm going to simulate this, or I'm going to show its output voltage. This is the output voltage. Before showing that, I have to say that the input current of this circuit looks like this circuit. We have the same input filter here. Same input filter here. And now the result of this controlling, again I'm going to this and show the result. You can see that this is the output voltage is regulated on 12 volts, and at 5 milliseconds, look at this, the output voltage is changed because of the change of output load and output power, but this converter can stabilize 12 volts on its output port again with this compensator, which is an average current mode controller. That's it. Before finishing this video, I'm going to talk about this. I found the small signals of buck and boost converter, and I used this both diagram to design my analog compensator. For example, this is the voltage mode controller of the buck. As you can see, the red one is for compensator, the blue one is for transfer function of converter, and the yellow one is the compensated converter. As you can see, I changed the cutoff frequency and this magnitude at low frequency here, and this is for voltage mode, and we have for average current mode. As you can see, again we have it for voltage loop control. This is for voltage loop control. The yellow one is compensated, the blue one is uncompensated converter, and the red one is the compensator transfer function. And this is for current loop. As you can see, the blue one is uncompensated, the yellow one is compensated, and the red one is the compensator transfer function. It is very clear that my converter can stabilize the output voltage on 12 volts properly by this compensator, average mode control, average mode current control, and voltage mode control.